In the last test block, we examined signals in the frequency domain. In this test block, we're going to look at systems in the frequency domain. And this is more complex than the signals. Signals are the nouns, they're the actual data. The systems are the filters, they're the verbs, they're the things that act and change one signal to another signal. And the way we describe a system in the frequency domain is with a transfer function. So this lecture is going to help answer the question, what exactly is a system transfer function? Let's start with a demo that models the system, and we'll see and hear how it modifies discrete time signals. We're going to look at what this arbitrary discrete time system does to a famous input. This is the most sampled drum solo in history. Wikipedia says it has appeared on over 6,000 tracks. It's from the track Amen Brother by the Winstons and improvised by Greg Coleman of Richmond, Virginia back in 1969. Unfortunately, despite this being one of the most famous drum solos, he received no royalties for it, and he died homeless and destitute in 2006 because the solo became famous after it entered the public domain. So here's the solo, and we're going to modify it with a low-pass filter. All systems have a transfer function that's composed of an amplitude and phase plotted against frequency. When a system is used to emphasize certain frequencies in music, it's called a filter. So here is this filter system transfer function. The amplitude is down here, and the phase is up here in the top middle. Now the amplitude here is on a linear scale. You can see this as a low-pass filter because it passes low frequencies here with a gain of about ×1, and it cuts these high frequencies with a gain of pretty close to 0. Not exactly 0, but pretty darn close. Now, more typically, the amplitude is plotted in decibels vertically, which is a logarithmic scale, and then it is called the system's gain function, and that's shown up here in the upper left. So here you've got 0 decibels corresponding to a pass, an unchanged pass, and it goes down steeply into the negative decibel region, which shows that it's almost entirely cut off down here. So let's change the cutoff frequency a little bit more. When the cutoff frequency is up high, around 22,000 hertz, we pass everything. You can hear all those high frequency sounds, the cymbal crashes. And as we start to cut the frequency, we lose those cymbal crashes. We can still hear the deep bass drum though. As we cut it still further, it sounds almost like we're underwater, and that's a very characteristic sound of a low-pass filter. Now we're losing the crash cymbals, the hi-hats, the toms. Eventually, all you hear is just the bass drum, maybe the snares a little bit. So now let's go back to the full sound, with the filter fully open. Now the bass drum and the snares dominate the sound, and the crash cymbals. Listen to the hi-hats. You can hear them going, but it's hard to hear them. Now, let's say you're a drummer and you want to learn to play that particular rhythm, but you can't make it out over all that other sound. Let's design a custom filter to bring out the hi-hats. Switch up here to custom, and let me begin by turning off the zeros. Take a look up here at what I'm doing in the upper right. You'll see I'm pushing out these poles. Now the poles are what emphasizes frequency, and the zeros are what cuts frequency. By putting the zeros in the middle, I'm taking them out of the equation. They don't do anything. The angle that the poles make are the frequencies that they emphasize. So I'm going to move this down and try to hear where we get the biggest snap. It's about here. Now I'm going to bring these zeros into play. I'm going to make them play a bigger role. And I'm going to pull them down to cut out the low frequencies. And now you can really clearly hear that click, 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 click of the hi-hats. Okay. So this is an example of a discrete time system in use, and the demo helps you hear intuitively what the system does to a sound. And it also shows you what the system's transfer function looks like. Here we can see it's a high-pass filter. It cuts out the low frequencies, passes high frequencies with an emphasis right around here, and then passes these frequencies much less. So this is the gain function in the upper left. And then we haven't really talked about the phase at all, but the phase is shown here. Now, next, we're going to see that this is just one of three perspectives to understanding what a system transfer function is. It's actually the third that we're going to discuss. So we're moving from last chapter, chapter 3, in which we discussed signals in the frequency domain. X of n and y of n moved over into the omega k or z domains. And this chapter is going to be on the systems instead in the frequency domain. So we're going to be talking about the transfer functions of the systems, the relationship between the inputs and the outputs. Much like the time domain stuff, this is a lot harder to figure out what a system is in the frequency domain than in the time domain. What was the way that we characterized what a system did in the time domain? Anyone?
We had like an h of t, which was like our transfer function.
H of n. Yeah. So that's one perfectly good way that we could characterize what a system does in the time domain, is ask what its impulse response is. Or more generally, what is its difference equation? So the discrete analog to the differential equation of the continuous time. And both those are correct answers. This exam block, instead of looking at the difference equation or the H of n, the impulse response, we're going to be asking ourselves, what is going on from the DTFT perspective of the transfer function, the DFT perspective, or from the Z transform perspective. And the big picture with all this stuff is omega is what we want to have, but the DFT is what we can compute, and we'll often go into the Z transforms because it makes it easy to work with block diagrams. But these two are very easy to change back and forth. All you need to do is swap a Z for an e to the j omega, and you can swap back and forth between the DTFT and the Z transform domain. Now that we've talked very briefly about the overview of chapter 4, let's talk about the three perspectives of what a system transform. Let's talk briefly about what a system transfer function is. Three completely different perspectives.